Okay, let's look at some partial fraction decomposition as it relates to finding antiderivatives. If you're an AP Calculus student, partial fraction decomposition is only in the BC curriculum. It is not an AB required component. However, a lot of teachers, myself included, like to show partial fraction decomposition to my AB students because a huge chunk of them will go to college and they will see it in college, and I want them to have some exposure. If you want to print a sheet to follow along, which is really nothing more than just a sheet with all the examples that I'm going to look at in this lesson, you can print that by going to this bit.ly link. It is part frac 1. That is the number 1. Because I will probably do another video with more complex partial fraction decomposition. This particular lesson assumes you already know how to do partial fraction decomposition. And in this particular lesson, we will only be looking at denominators that can be factored into linear, non-repeating factors. Those are the easiest types you can possibly get. And that is all you will see in BC. However, I will still show my students some more complicated techniques because, again, it's good to see them before you go to college. And I will be using something called the heavy side method to perform the partial fraction decomposition. If you don't know what that is, you're going to learn it in this lesson, and it is quite sexy. And that is spelled heavy side this way with a capital H because it is a mathematician's name. It has nothing to do with the weight of a problem or which side of the equation you are looking at. It's just the heavy side method because Mr. Heaviside is the one who popularized it. So let's look at question number 1. And before you dive into more complicated techniques like partial fractions, you always want to consider things like U substitution and some easier options, maybe recognition. And I see nothing on this one that will work. Also, an indication that you will use partial fractions is that your denominator factors, and this denominator does indeed factor. I think I just spit on my finger. That was fun. And so that denominator factors to x minus 2, x minus 3. And if those are the factors of the denominator, that means we started with two fractions, or we can break this up into two fractions whose denominators are x minus 2 and x minus 3. And what I don't know is what the numerators are up here, and those will be constants, a and b. Our challenge here is to find the A and find the B. And there are a lot of methods, and they may be safer mathematically because you are using more of a mathematical process. Heaviside's method is a little bit more of a shortcut, and it's cute, but boy, is it convenient. And so I'm going to use it. There are some times where I feel the cuteness and the memorized methods are so much more efficient, it's worth using. And what we're going to do is we're going to look under the A, and I see an x minus 2, and you're trying to figure out what value of x makes that equal to 0. Well, that's obviously x equals 2. Then what I'm going to do, I'm going to go ahead and get A in one step. Excuse me for a sec. Okay. All right. And that one easy step is to go back to the fraction where you factor the denominator, and we will cover up the factor that gave us the value of x equals 2. Cover that up completely. And a lot of people, teachers will call this the cover-up method for that reason. And we find out that A is, and we get A by plugging 2 into all remaining x's, which means we have 1 over 2 minus 3, which means A is negative 1. And then we will repeat that process for B. Get that out of the way. I'll look under my B, and B, the factor that, or the value of x that makes that 0 is 3. And so to get B, I will plug 3 in for every x except for the x where I got the value of 3. So I'm going to cover up that factor. B is going to be 1 over 3 minus 2, which is just 1, which means this problem, which was the antiderivative of 1 over this quadratic thing, can now be split up into two much easier antiderivatives. It'll be the antiderivative of A, which is negative 1 over x minus 2, plus the antiderivative of B, which is positive 1 over x minus 3. And both of these are going to be incredibly nice because we now have fractions. And anytime I'm doing the antiderivative of a fraction, the very first thing I'm going to look for is, can I make the numerator the derivative of the denominator? Because if you can, then we have a natural log. The second one is very clearly a natural log. The derivative of x minus 3 is 1. So the antiderivative of that second piece will be the natural log of x minus 3. The first one, derivative of x minus 2, is 1, not negative 1, but I can fix that pretty easily by simply taking that negative, and we can pull that out of the problem like this. So it's negative 1, and the antiderivative of 1 over x minus 2, which makes this negative natural log of x minus 2. And then in any general antiderivative, you always want to put a plus c. So there is your antiderivative. And it's really not that bad. Partial fraction decomposition is kind of intimidating because you probably had problems in pre-cal where you had like 14 letters you had to solve, you had to set up matrices and stuff. In the context of calculus BC, the decomposition is pretty convenient. That said, I do want to do one more thing with number 1 that you will probably have to do, especially if it's a multiple choice question. And you can rearrange these just to make it a little bit nicer, I guess. That's the same thing as natural log of x minus 3 minus the natural log of x minus 2. And in multiple choice questions, College Board, the people who write the AP exam love to use properties of logarithms. And if you're subtracting 2 logs, you can combine that into a single log where you divide their arguments. So I'm going to change that to the natural log of x minus 3 over x minus 2, a single logarithm with that argument. The plus c hangs on the outside. And you don't have to do that in free response, but this probably won't be free response. It'll probably be free multiple choice. And they love to combine your logarithms at the end of partial fractions using these properties. So once you see logarithms show up in a multiple choice question, just go ahead and turn on the part of your brain that is housing those properties, because you will probably have to use them. All right, so let's look at number 2. Let's see number 2. Again, first thing I'm going to look for is, can I factor the denominator? And you can, because that denominator will factor 2, x plus 2, x plus 9. And oh my gosh, how nice is this? How nice is this? I forgot this did this. I think I did this on purpose. The x plus 2's cancel, right? Now, if you wanted to do the full partial fractions, you could. It will be unnecessary. Those cancel. This turns into just the antiderivative of 1 over x plus 9. And that would be the natural log of x plus 9. The only thing you want to be careful with, and it doesn't matter in this particular problem, we're done, that's our answer, is when you factor and you start canceling factors out, you do have to keep in mind a little bit of pre-cal, some continuity issues. There is a removable discontinuity, also known as a hole at x equals negative 2, because we factored out that x plus 2. If this were a definite integral, that hole might come into play. I don't know. Really, an indefinite integral, it still wouldn't have even mattered because it's just a hole. It's not an asymptote. But any time you make cancels or you change your equation like that, just keep in mind of any potential domain issues that are created. It really doesn't matter here. I just wanted to remind you that certain things like that do exist. Let's go on to 3. So 2 over x cubed minus 9x. This is a little bit of a complicated, ugly problem. I'll leave my numerator as 2. The denominator, if you factor out an x, we would have x squared minus 9, which then continues to factor to x plus 3x minus 3. Which means I started with 3 fractions. One denominator of x, one denominator of x plus 3, one denominator of x minus 3, and we need to solve for a, b, and c. By the way, a little piece of advice, your denominator, the degree of your denominator before you started factoring, well, even after you factor, but the degree of your denominator tells you how many letters you are going to be solving for in the numerators of your split up fractions. So those constants a, b, and c have 3 because the original degree was 3. So in the more complicated partial fraction problems, which I'm not going to get to in this lesson, that is a little bit helpful. So like if you know you're going to have 4, then go ahead and be ready for an A, B, C, and a D. And that may help you in the more complicated where you have nonlinear or repeating factors. But again, that doesn't matter here. I'm going to go ahead and solve for my A, B, and my C by looking at underneath my A, and I can have x equals 0. We'll make that denominator 0, which means that A is going to be, I'm going to go over here, I'm going to cover up the factor that gave me that value of 0. A is going to be 2 over 0 plus 3 and 0 minus 3. So that'll be 3 times negative 3. A is negative 2/9. That's kind of ugly. B, by the way, I need to restore my fraction over here. B, x equals negative 3 is going to give me a 0 under my b. So that means b is, I'm going to go over here, cover up the factor that was under the b. It's going to be 2 over negative 3 times negative 3 minus 3 is negative 6. 2 over 18 is 1/9. And then C, I need to restore my original problem. So let's get that out of the way. And for C, we'll plug in 3 for x. Cover up the x minus 3, plug in 3 for all of the remaining x's. And we have 2 over 3 times 3 plus 3. 3 times 2 over 3 times 6 does clean up to another 1/9. Did I do that right? Because I was expecting something different. Okay, I think that's good. And now I can reset my original problem. It's now going to be the antiderivative. Instead of 2 over x cubed minus 9x, it's the antiderivative of negative 2/9 over x for a over x. I'm going to go ahead and close off that antiderivative, and then I'll set up another one with b, which was 1/9 over x plus 3. I'm going to have to close my blinds over there. The glare on my windows, sun setting. Plus c, which was 1/9, all over x minus 3. And now we have those 3 antiderivatives. And in these cases where you have linear non-repeating terms, they'll always end up being a natural log. That's kind of convenient in the BC context. Again, when you get to college and in more complicated problems, be ready for other integration techniques. But in all 3 of these, you can take these constants out, make that negative 2/9 times the antiderivative of 1 over x, plus 1/9 times the antiderivative of 1 over x plus 3, plus 1/9 antiderivative of 1 over x minus 3. Okay, fix that glare. And when you pull those constants out, you then get these 3 antiderivatives here, negative 2/9 of that integral, the ones that I just mentioned a second ago. And then once it looks like that, now I can very clearly see that in all of these, my numerator is the derivative of the denominator, 1 over x plus 3, 1 over x minus 3, which means all 3 of those do turn into natural logs when you find their antiderivatives. And you could do some magic with these constants in front to turn this into a single logarithm. This one's a lot more ugly and complicated, so I'm not going to bother on this one. It's usually only done when it's relatively convenient to combine your natural logs. So let's look at number 4 here. And if you look at number 4, the denominator does factor. You can factor that denominator into x plus 7x minus 5. However, before you just dive into partial fraction decomposition, you always want to consider other options because they tend to be a little bit quicker. And this is one of those. This one we can actually do u substitution. If you consider that denominator, if u is x squared plus 2x minus 35, the derivative of that u would be 2x plus 2 dx. And the way I do substitution, and other teachers may use a slightly different method, it's all essentially the same thing with different representations on paper. I like to find that du in the problem. What I currently have is 4x plus 4 times dx. I need a 2x plus 2. I can turn 4x plus 4 into 2x plus 2 if I multiply it by 1/2. Well, if I multiply the inside by 1/2, I need to offset that by also multiplying by 2, because 2 times 1/2 would be 1, and I'm going to put that 2 out here. And once I make that change, now my numerator is the derivative of my denominator, which means this answer, the 2 on the outside, is going to stay. Once the numerator is the derivative of the denominator, your final answer is 2 times the natural log of the denominator, x squared plus 2x minus 35. If you went through the partial fraction decomposition process, you will have an answer initially that looks a little bit different than that. And you can use those properties of logs to manipulate it to turn it into a single logarithm, which would ultimately take you back to this answer. So if you do partial fractions, you're creating a little bit more work for you because the answer in a free multiple choice question, I would think it'd be this. They may make it the natural log of the product of x plus 7, x minus 5. That could be how it's presented. But just always look for easier options before you just dive into more complicated methods. And then number 5, 1 over x squared minus 10x plus 41. And this one looks like a partial fraction problem. It does. However, if you are trying to factor that, you will see that there are no factors of 41, at least integer factors, that will add to negative 10. And so if it doesn't factor, that means partial fractions doesn't work. And the only reason I'm throwing this in my partial fractions lesson is because I don't want you to think that it's a one size fits all for these. You always have to remember other options. And I think if you're in partial fraction territory of the calculus curriculum, you have already been exposed to this. If the denominator doesn't factor and my numerator is not the derivative of the denominator, which it's not, I can't turn a 1 into a 2x minus 10. We're going to solve this one through completing the square. And this is just a reminder. I mean, if you only care about partial fraction decomposition, you can stop watching right now because this is not, and I believe this is the last example, isn't it? Yeah. But I'm going to solve this through completing the square. I'm going to separate that plus 41 over here. And if I complete the square, half of negative 10 is negative 5, squared is 25. But if I add 25 to my problem, I have to offset that in the same way that I had to offset the 1/2 that I put in here. I have to use its inverse, and the additive inverse is just making it negative. So that'll be negative 25 out here. I'm going to subtract the 25. And the whole point of completing the square is that allows me to factor that as a perfect square. So that's x minus 5 quantity squared. 41 minus 25 is 16. There's a 1 on top. And now this resembles your inverse tangent derivative. And this is one that I give my students a nice little memorized formula for inverse tangent. That'll be u prime over a squared plus u squared. Does give you the answer in the antiderivative. Boy, I said that really weird. It's 1 over a inverse tangent of u over a. And the reason I do this through a memorization process is because there are times where the memorized formulaic method is so much more efficient than working it out another way that I think that I prefer memorizing. I don't memorize stuff very often, but in this case, my function that is being squared is x plus x minus 5. So u is x minus 5. My a is the square root of that number. So a is 4. My u prime, the derivative of x minus 5 is 1, which is exactly what I already have up here. I don't have to do any changes. So this one's already set up to use this little template. And so we're left with 1 over a inverse tangent of u, which is x minus 5 over a. A is 4, plus a c, and we are now done with that one problem. So I had a few examples in here that ended up not needing partial fractions, but there we have it.